All right, for number one, based on this description here, let's talk about this first set of brackets here. So generally speaking, when x is close to 3, is y increasing, decreasing, or staying about the same?
Decreasing?
I'm sorry, what was that?
Decreasing?
Okay, I got one vote for decreasing. Anybody else?
Yeah, I'm also going to say decreasing.
Okay. So yeah, we are told that basically here's the concise mathematical way to represent this. Dy dx is equal to -8. So y is decreasing as compared to x. So next one here. Is this decrease happening slowly, moderately, or quickly? What would you suggest?
Quickly.
Okay, I got one vote for quickly. Anybody else?
Quickly as well.
Okay. So got a couple of votes for quickly. Why are we saying quickly? What gives us that conclusion?
-8. It's a decently large number.
Right. So it's a pretty steep slope, this -8 here. So let's go ahead and circle that. And just to put a bow on this, what about this rate says that it's decreasing?
A negative sign.
Yeah, negative sign. So yeah, the negative sign shows a decrease. And then the quickly comes from that's a steep slope, -8. All right, any questions on that first one before I scroll down and clear out my drawing?
How do we know that dx dt is positive in this case?
Do we know that dx dt is positive? Well, if you're looking ahead to number 2, that's a completely different situation.
Oh, I mean, I was talking about number 1.
Yeah, number 1 stops right here. Okay, let's go ahead and clear and move on. So 2, 3, and 4 more or less go together. So I'll just stop right here. I'm going to give it to you all for the next few minutes to think about these. Do me a favor here. When you are ready to move on, do me a favor and send me a private message on chat. Yeah, take a few minutes, and when it sounds like at least most of you are done, I'll take some questions. All right, let's go ahead and talk about these next few. All right, number 2. So at this moment, we're t equals 5 seconds. Dx dt equals 3. So what does this mean?
At t equals 5, the rate of change of x with respect to t is around 3 for
Okay.
that small interval.
So what was your last bit there?
For the small interval.
Okay. So for a small interval around this. Anybody else have anything a little bit different? So near t equals 5 seconds. So I know let's just say it more mathematically this time. We know that basically x the rate of change of x with respect to t is 3, but I want to use units. So 3 what?
Centimeters.
Okay. So I got a couple of votes for centimeters. So here are the things I'm thinking about, or that you guys are suggesting. Got centimeters, centimeters per second, centimeters per t. Remember dx dt, that any rate of change needs to unite two quantities. So since x is represented by centimeters and t is represented by seconds, then really our rate needs to reflect that centimeters per second. Any questions on that first one? All right, pretty similar idea for 3 here. At this moment, I have dy dt equals -3/4. So again, near t equals 5 seconds. Now let's try to say this one a little differently this time. You know, I could clearly just kind of mimic this this phrasing here. The rate of change of y with respect to t is -3/4. But let's kind of try to describe in more plain English what's happening here. What does y refer to? So Tony says the particle's vertical movement. So we're almost there. So that in the y coordinate, basically, yeah. So that's some vertical position of this particle. So I'll say the particle vertical position is doing what? What's it doing at this moment?
Decreasing.
It's decreasing. At a rate of 3/4 and same units this time, 3/4 centimeters per second. Any questions on 3? All right, moving on to 4 here. Find the value of dy dx at t equals 5. So how do we find that?
We could just put dy over dx, right? The values we found.
You said put dy over dx, so let's be a little more clear about that.
Would it still be dy over dt over dx over dt?
Yeah, we can absolutely do that. So, and I'll spell this out a little more. You know, if we kind of manipulate some stuff, we have dy dt times dt dx. And so I think that makes it a little more intuitively clear that, yeah, that we're going to indeed get dy dx about this. So dy dt is -3/4. And dx dt is +3. So what is this going to come out to?
-1/4
-1/4.
centimeters per second.
And I got to vote for centimeters per second again.
Can you quickly explain why it's centimeters per second? Like for this one, I understand like 2 and 3.
Yep. So do you all agree that the unit should be centimeters per second again?
Don't the units cancel out in a way?
Yeah, so let's go backwards a bit. I know that these individual rates, you know, this is dy dt, this is dx dt. Those are certainly centimeters per second, right? So I'm only going to write this to explain what comes afterward, but now what I really have is -1/4 centimeter per second per centimeter per second, which is a mouthful. But hopefully you can see there that these units will cancel. So basically at this -1/4, this is a unitless quantity here. Does that make sense?
Yeah.
So let's think about that just a little further. Let's think about why that happened. dy dx. What does dy dx mean? So Rodolfo says it's a ratio or a slope. Let's be a little more specific though. I mean, all of these things are ratios. And I could really even say they're all slopes if I, you know, graphed the right thing. So for example, if I had some graph here where this is the t-axis, this is the x-axis, you know, I could talk about the slopes of this curve, or I could draw tangent lines to this curve, things like that. So what specifically, actually, let me go back a little bit. You know, we've talked all semester long about derivatives and antiderivatives and, you know, applying those things. But really a derivative is just a rate of change. And for most of the semester, we've just been talking about two quantities, x and y, or what, you know, just whatever those two quantities are, some independent variable and some dependent variable. So when you say the rate of change, you know that you're uniting those two quantities. We're not really in that situation anymore because now that we're dealing with this third variable, this parameter t, you can't talk about the rate of change without being a little more specific. So now I'm talking about the rate of change that joins these two quantities, y and x. So let's interpret that. What is dy dx? What rate of change is that talking about?
The rate of change of y with respect to x.
Right, and that's right. What do y and x represent?
Centimeters per second.
So you said centimeters per second. Is there a time component to dy and dx? And Tony said that y is represented by centimeters and x is represented in centimeters. So remember, there's a pretty fundamental difference between these two things, dy and dy dt. Now dy is just a small change in y. Dy dt is a rate of change of y with respect to t. So basically what this rate of change here says is, you know, as this particle moves to the right, by how much does it move upward or vertically. So basically, you have a rate of change of the particle's vertical movement to its horizontal movement. Any questions about 2, 3, or 4 before I move on?
Is slope just like a messy way to just say rate of change in that case? Because you said like -1/4. It's like the x movement and the y movement, and
Yeah,
like,
so I mean-
slope is just rise over run.
Yeah, and so yeah, this -1/4, I'm not going to graph it out or do anything like that right now because that's something we're going to do later. But yeah, basically that -1/4, that is the slope of this curve if we were to graph it out in y versus x. That -1/4 would be the slope, but we don't know what the slope is going to be at any other place. We only know it at this one value of t, which is equal to 5. And Tony's asking to confirm there's no units for 4. That's correct. Yeah, this rate right here, -1/4, that's a unitless number. Any other questions about this? All right, let's move on to number 5. All right, same drill. Go ahead and send me a private message when you're ready to talk about 5. All right, let's go ahead and talk about this one. So I'm going to go ahead and, I'm not sure if Mark has extensively used this notation, but it says the same thing. There's a second derivative of y with respect to x. Right, so we have the second derivative of y with respect to x is -1. So what does this mean? Okay, Tony says the rate of change of the slope. So the rate of change of the slope, which I guess, yeah, I mean, we can think of dy dx as the slope. So my only clarifying question would be to Tony's answer would the rate of change of the slope with respect to what? Rodolfo says the second derivative tells us the rate of change of the rate of change. So in this case, the rate of change of the rate of change of y with respect to x. And that's, I mean, those are both really close. A lot of good information there. So, and specifically, Gabrielle says that rate of change is decreasing, given by this -1 here. So, one thing I want to point out is that, you know, a derivative, it doesn't matter what the derivative is of. A derivative tells you the rate of change of that function, whatever the function is that you were differentiating. So think about the way you take a second derivative. To find a second derivative, basically what you do is you find the derivative of the first derivative. So absolutely, you're just finding the rate of change of that first derivative with respect to x. So this tells us basically that the rate of change of dy dx, you know, which we already deciphered, kind of talked about what dy dx represents in the last question. The rate of change of dy dx is -1. All right. And Noonzeal says the rate of change of y with respect to x with respect to x. I think that I agree with you that, I mean, it's the, I think you and I are on the same page with the wording is, yeah, I'm not totally sure, but I believe that you and I are saying the same thing. Basically, but I think just to clear it up a little bit, the rate of change of dy dx. So yeah, the rate of change of dy dx is -1 with respect to x. So basically, as x in this vicinity, as x increases, dy dx will decrease by 1. Any more questions about 5 before I move on to 6? 6 will take us maybe to the end of this period here. I want to make sure we're all okay on the first 5, or I guess these last 4 before we move on. All right. So number 6, basically what we're going to be doing here is graphing what we have. So I'm not sure if I emphasized this or pointed out, but this function p right here, basically that is giving us all of our x values. And the function q of t was giving us all of our y values. So all we know for right now is that we have this point -2, 2. So remember, everything we've done so far has been around this t value of +5. So around 5 seconds, we have this x value -2, y is equal to 2. And let's just write down, you know, the information we've collected so far. We know that dx dt is equal to, was it -3/4? I think I remember that, but I'm just gonna, if someone wants to correct me, they can. Now that I'm looking at it, I'm pretty sure I have these backwards. Thanks, Tony. And then from there, we found that dy dx was equal to -1/4. And we also just found that d squared y over, or we didn't find this, we were given this, is -1. And all of these were at, in the vicinity of t = 5, which is the same vicinity we're looking at here. One more thing I want to point out is that we're assuming the second derivative is constant for values of x within a radius of 1 from the point, this starting point here. So basically, all we really have any hope of doing here is graphing this, for the x values that are within 1 of this point. So that's the only time we know anything about this d squared y dx squared. So basically what we need to do now is graph this, the rest of this curve over whatever interval it makes sense to graph it for. So here's what I'd like you all to do. Go ahead and try that on your own. And in a few minutes, I'll ask for people to start annotating my screen. But yeah, just based on the data you have, start trying to draw that graph. If you have any questions, go ahead and please ask them of the whole room. So either whether you ask your question on chat or verbally, yeah, please ask it for the benefit of everyone. This is a little bit trickier than the last things we've done, so I think it would be helpful if everyone was aware of the questions and the answers. But I'll go ahead and, are we drawing the functions by taking antiderivatives? Rodolfo, you can, but I don't think that's necessary. If that helps you, you can absolutely do it that way, but I don't need this to be, for our purposes here, we don't need to be totally exact. We're just, we're going to try to sketch it as closely as possible. So you can take antiderivatives if you want, but I don't think that's totally crucial for the level of accuracy we're doing right now. All right, no rush, but if you're ready to show me an annotation here, go for it. Otherwise, we have plenty of time to keep working on it. If anybody has any questions or would like a nudge in the right direction, feel free to ask. people able to annotate on my screen? So since I don't have any information about the second derivative outside of this interval, I'm just going to draw these dotted lines to show that I can't really graph outside of here. So basically, you're all not responsible for, you can't really graph over here or anything out here. Basically, all we really can do is, all we can really sketch is inside this interval here. Does anybody have anything they're willing to share? Yep. So let's, just in the interest of time, let's kind of just build it up from here. So I know this point here. I know that that's my starting point. So let's talk about this. As I move to the right, so as x increases, is my graph going to go upward, or it's going to stay kind of horizontally, decrease? What's going to happen? What is my graph going to do as I progress to the right from there?
At the very beginning, it's going to decrease, is going to go down to the right, correct?
Right, and how do you know that?
dy dx is -1/4. So as x increases by 1 unit, y will decrease by 1/4 of that.
Right, so I know that my dy dx starts off being negative. All right, now, so in just a, and actually, in fact, that's a little steeper than I think I want it to be. So it's going to be rough, but that's fine. So now what happens if I go a little further? Is it gonna go back up? Is it gonna kind of stay on that same slope? Is the slope gonna get even more steeply negative? What's gonna happen now?
I have a question. So like the second derivative, since it's -1, would that
Mhm.
mean the rate of change goes even more negative, or would that mean they cancel out and it goes back to
No,
positive?
that's exactly what it means. It means that I'm gonna get even more.
Okay.
So we know that my slope dy dx started off as negative. So as x gets bigger, the second derivative tells me that the slope is going to continue to decrease. So you're going to have a curve that looks something, I don't know how drastic this is going to be, but I know it's going to keep decreasing. Are we okay with that?
Yes.
So now let's go to the left. Starting from our starting point here, and as I go to the left, this curve going to go upward, horizontal, going to decrease. Like what's going to happen?
Would it increase going to top left?
Yep. What tells you that?
Dy over dx.
Yep. So dy dx is negative, which means if x decreases, then y increases. So is it going to continuously go up like this? Is it going to come back down a little bit? Is it going to kind of stay on that heading?
It's gonna increase increase more.
So I got one vote for it's just going to keep going up to the left.
Yeah, I think it'll just continually increasing as it goes left.
Okay. Got another vote for that. Anybody else? So something to pay attention to, the d squared y dx squared, that second derivative. That second derivative is negative. So what I want to happen as I move to the left, as x decreases, I want my slopes to be constantly decreasing. So that means I'm going to have something that looks like this. Let's just take it back to this initial point here. Our slope is initially -1/4. But let's say if we go back towards the left, everywhere on this interval, my slope, my dy dx is decreasing. Which means as I go to the left, and I should be more specific about that, as I go from left to right, so with x increasing, my slope dy dx is going to be decreasing, which means the opposite needs to be true if I go to the left. As I go to the left, the slopes need to be increasing. So right here, what do we say the slope was?
-1/4.
-1/4, which means if I go backwards from there, I should eventually hit a place, and I don't know this is the exact place, but I should eventually come to a point where the slope is 0. We okay with that conclusion?
So I have a question. So I understand, like, how it goes up a little, but I'm still not too sure why it goes back down. Does the second derivative just overrule everything?
Yeah, I mean, like I said a little bit ago, your derivatives always tell you the rate of change of whatever that that more fundamental function was. So whatever function you differentiated to get the derivative tells you the rate of change of that function. So the only thing we know about this graph though is that the second derivative is constant. So basically this second derivative here, this is good for x between -3 and -1. I only know the first derivative at -1/4. I don't, before I had this information, I did not know what, I had no way of knowing what the slope would be of my curve at anywhere other than this point. In fact, and the only way I can find out what that slope is by knowing the second derivative. As I move to the left, I know that slope will increase. As I move to the right, I know that slope will decrease.
And how did you know the parameters of -3 and -1?
From this clause or this phrase here, the second derivative is constant for values of x within a radius of 1 from the point in question. So
Oh,
the
okay.
point that we started with was x equals -2. So one left and one right of that is -3 and -1. Any more questions about this? All right, I'm gonna go ahead and stop sharing. I have 350. There is a quiz today. It is open until 11:59, but if you want to go ahead and take care of it now, it's already been published. I'll stay in the room for a few minutes in case anybody has any questions. Otherwise, I'll see you all in class tomorrow morning.